Yeah, so yesterday we were talking about how acids are and what bases are, and how the definition of acid and base tells us what they behave like. So, ionization is a process that involves in the definition. Basically, we're saying that any acid, it will ionize, it will produce H positive ions. But the extent of that ionization, like how many molecules actually ionize, that depends on whether it's a strong acid or it's a weak acid. If it fully ionizes, then it's a strong acid. If partially ionizes, it's a weak acid. What that means is that not all of the molecules are ionized. Okay, so while they all have H positive ion, not all of them are losing it at the same time. What that means is that partially ionized, the weak acids, they react slowly even if they have the same concentration. Okay, and we have indicators that can help us figure that out. So universal indicator allows us to measure pH. So that's a way of measuring pH, that basically you have a pH scale which goes from 1 to 14, and 7 is where it is neutral. So 1 to 7 is the portion where you have more H positive and less OH negative. And on the right side of that, from 7 to 14, you have more OH negative and less H positive. So that's what makes it basic. Obviously, in the middle, you have equal amounts, equal part H positive and equal part OH negative, and that's what water is. So we know that water is neutral. Now, that is one way of figuring out whether an acid is strong or weak. You simply put the universal indicator in there and you match its color with the chart. So there's two parts there. First is you dip the universal indicator paper or pH paper, or you can put a couple of drops of universal indicator in the solution or a portion of a solution, and then match the color with the chart. So it's important that you mention both of those things. Okay. Now that will allow us to measure whether it's a strong acid or a weak acid. There's another way to check whether something is strong acid or weak acid. You simply pass electricity through it. And if the current is high, that means there is more flow of electricity, then that is a strong acid. And if the current is low, or if the bulb is not as bright, then that shows that it's a weak acid. So these are two different ways of checking whether something is a weak or strong acid or base. Now, there are other indicators that simply allow us to differentiate between acids and bases, and that is phenolphthalein, which is colorless in acid and pink in base. Methyl orange, which is yellow in most acids, and base in bases it is red. It is orange for some extent, but we do not say that, we skip that part because it does not qualify that okay it's for acid or for base. There's a whole range of pH where it is orange, so we don't talk about it. Similarly, litmus, it is red and blue, and it's red in acids and base in bases it's blue. So we use it to check for ammonia. Ammonia, as we know, is a basic gas, and so if you have red litmus paper, it will turn blue if you have ammonia. Now, obviously, if that paper is damp, then it will absorb ammonia more. And that is why usually when we are testing for ammonia, we use damp red litmus paper. Red because we want it to go to blue to confirm whether we have ammonia, and damp because water allows us to absorb more ammonia gas. Now, how does ammonia do that? Ammonia basically bonds with an H positive ion, and we say that it has accepted an H positive ion to make ammonium ion. Now, important thing to remember here is that this is covalent bonding. Ammonia is bonding with an ion through covalent bonding. So that's a very unique case as far as O-level syllabus is concerned. That ammonia, which is made from non-metals, it's forming another covalent bond with a non-metal, but it will create an ion because that H positive is an ion itself. So covalent bonding makes ammonium. Now that ammonium is ion, which means it will further do ionic bonding with things. So ammonium chloride is ionic, but within that ammonium thing, within that ammonium ion, we have covalent bonding. So sometimes there was this MCQ once, that which of the following compounds has both ionic and covalent bond. So that answer included ammonium because ammonium has covalent bonding in itself, but when it joins with other things, it joins as ion, forming ionic bond. All ammonium salts, if you have ammonium ion, it will lose that H positive and it will create ammonia, which means that if I have ammonium ion, I can heat it up to let that ammonia go. because particles have more kinetic energy, they collide more, and so it is easier to lose that ammonia. Similarly, because they lose H positive, we can say that ammonium salts are acidic. Ammonia gas absorbs H positive, it reacts with H positive, it accepts H positive. So ammonia gas is basic, but ammonium ion is acidic, which means all ammonium salts that you have, ammonium chloride, ammonium hydroxide, whatever you have, they're going to be acidic. Okay. And they're all soluble in water as well. So that's another thing that you should remember. All right, so let's see what acids react and what are their characteristics. So acids basically have H positive, and that is the main key through which they react, or that you have to focus on when they're reacting. What this means is that if something is more reactive than H, it can simply come and replace it because you have an H positive ion. So that's exactly what happens with most metals that are reactive. So you have an acid and you add a metal to it. That metal, depending on whether it's more reactive than hydrogen, it's going to replace it and liberate hydrogen gas. So that's a gas. So equation में ही हमें पता चल रहा है that we are getting a gas, so there will be bubbles. So we can guess those observations just by looking at the equation. That we can say that when this reaction occurs, we will see bubbles. And this is hydrogen gas, so we know that you can test hydrogen gas by popping it in a flame. Then if once you get hydrogen gas, the other thing you get is salt, and that means metal dissolves or metal disappears because it has reacted. Obviously, if you add extra metal, then all the acid will simply uh, react. So we'll say that acid is the limiting reagent. But if you add less amount of metal and acid is more, you will see that all the metal has disappeared. So that's another observation. So two observations in this reaction, that metal disappears and bubbles of hydrogen gas. Obviously, you cannot say just by looking at it whether they are bubbles of hydrogen gas or some other gas. So that's why we always test the bubbles that are coming in. And the test for hydrogen is that it pops in a flame. Now, I'll give you an example. Let's suppose we have sodium and I put a block of sodium, a small piece, in, let's say, HCl. Now, HCl is aqueous, which means it has water in it, and sodium is solid. Now, what happens is that sodium is going to react with it. Because sodium is more reactive than H, it's going to replace it and it's going to form this. Now, judging by this equation, can you say whether this is redox or not? Is this a redox reaction or not? So remember that one simple way of checking whether something is a redox reaction or not is that you have an element on one side and that element doesn't remain an element later on. So on the other side, you don't have that element in the element form, I mean. So here you can see that sodium on the left side is as an element. Yes, Noor, you're absolutely right. This is redox. So on the left side, you can see that sodium is an element, but on the right side, sodium is no longer an element. It has actually reacted and it has formed sodium ion. Okay, so that shows that this is redox. Similarly, you can see that hydrogen, which was an ion, a cation, and it was aqueous before, has now changed to hydrogen gas, which is an element, and that also shows that this is redox. Now, how exactly do we know that this is a redox reaction? For that, we have to make what we call an ionic equation. Okay, so for ionic equation, we did that earlier on as well. What do? You ionize only the aqueous things that dissolve in water. So that's one thing you have to remember. How do you write ionic equation? You write everything as it is, all the pure things as they are. So sodium remains as sodium, and hydrogen remains as hydrogen. So solid, liquids, and gases don't change. What happens to HCl here, because it is dissolved in water, that means it will ionize. So you write its ions. You don't write the whole compound, you write the ions. Similarly, sodium chloride, it is ionic. So we'll write sodium ion and chloride ion. So that's how it changes. Now, if you notice, there is sodium, which went from sodium to sodium positive. So because there's an increase in oxidation state, we will say that sodium has been oxidized. Sodium went from 0 to sodium positive 1. So that is oxidation. Hydrogen, on the other hand, went from hydrogen positive plus 1 to 0. Obviously, I didn't balance this equation, but you can check it without even balancing that this is reduced, and that is because it went from +1 to 0. Now, the third thing, chloride, it did not change at all. Chloride remained as a chloride ion. So we'll say that this is spectator, okay, and this is reduced, and this is oxidized, okay. So most acid-base reactions are actually like most reactions of acids and metals, all of them are redox. Now, what kind of metal will react with acid but a little slowly? Any acid that is closer, any metal that is closer to H positive in the reactivity series. So let's suppose you have iron. So if I put an iron piece of iron in HCl, let's say, it will produce iron chloride. Sure, it will produce hydrogen gas, but this reaction is going to be much more slower than the reaction between sodium and HCl. Okay, and that is because iron is a bigger atom. It takes more energy to lose that extra electron. Sodium is a smaller atom comparatively. Sodium is also losing just one electron. Iron is losing two electrons. So multiple reasons here, but all of them point to the fact that sodium is more reactive and iron is less reactive. Okay, so you will see that while bubbles are also formed in this one, but these bubbles comes much more slowly, or the rate of reaction is slower compared to the rate of reaction of sodium. So let's suppose they gave you two different pieces of metal and they're like, okay, find two chemical methods to figure out which is sodium and which is iron. So one chemical method would be that you simply reacted with any acid of known concentration. Now, if they both react with the same acid, same concentration, sodium is going to react much faster and iron is going to react slower. Now, I don't know whether they have cancelled paper 4 for, they have taken an exemption for your school or not. So I'll just tell you that for paper 4 or in IGCSE paper 6, you may be asked to write these experiments or may be asked to design these experiments. Okay, so usually these exam design, experimental design questions are 4 to 6 marks. So this could be a question there that how will you differentiate between two pieces of metal based on their reactivity? So this could be a possible solution that you react them with an same acid of same concentration, the one that reacts faster, which means the bubbles are coming much faster. The amount of gas that is collected much faster than the other metal. So that tells us that so one metal is more reactive and the other is not as reactive. Similarly, we can use the same reaction to differentiate between, let's suppose, iron and copper, because copper is less reactive than H positive. So if I put it in acid, now I'm taking example of HCl. It doesn't have to be HCl. It could be H2SO4. It could be HNO3. Any strong acid would do. So if I react with that, the reaction will not happen. Reason, because as long as I have dilute HCl, copper will not react because copper is less reactive than H positive. Now, if I had strong acid and it was concentrated like H2SO4 but concentrated, HCl but concentrated, not dilute, then copper will react. In that kind of reaction, for example, with sulfuric acid, sulfur dioxide gas is evolved. But the only thing you need to remember for this, for O levels or IGCSE, is that copper reacts with concentrated strong acids. So now write it down somewhere if you want to. That copper reacts with concentrated strong acids. It does not react with dilute acids because it is less reactive than H positive. Okay. So that's a fact that you need to remember. So if I gave you copper and iron and I asked you to differentiate between them, and I ask you to differentiate using two physical methods. One method would be that copper is pink and iron is gray. So there you go. That's a physical method. You can identify it based on the color. But the same color can also be used for a chemical method. For example, if you told me that copper's ions are blue and iron's ions are red or green, then that is not a physical method. That is a chemical method that you have told me, because now you have basically converted metal to ion. So pay attention to these things, that if you are just using the color of that thing as it is, then it's a physical method. But if you have changed it to an ion or something, then it's a chemical reaction. And so a chemical change has occurred and it's a chemical test. Similarly, another way to test would be you put them both in the same acid, let's suppose dilute acid. Copper will not react, but iron will react. Okay, so that is the reaction of acid and metal. Metal will dissolve, that's an observation. Bubbles of hydrogen gas come in that we can test, and copper will not react. It is a redox reaction because the metal, because it's more reactive, it is oxidized, and hydrogen, because it is less reactive, it is reduced. All right. So, any questions there? Okay. So let's move on to how does an acid react with a base. Now that is pretty simple. Acid is going to lose H positive. Base, if it is an alkali, then it's going to lose OH negative. So if you have an acid and you have an alkali, what is an alkali? It's a water soluble base. It's going to produce water and salt. How does that work? Basically, acid is going to lose H positive. So let me just say it is HA and BOH. So this B is not boron, it is simply anything. So what will happen is that this H and this OH will react to make water, and that A and this B are going to react together and make BA, that's a salt. So I'll give you an example. HCl plus sodium hydroxide. It is simple reaction. HCl is going to lose H positive. Sodium hydroxide is going to lose OH negative. And so they're going to come together and form water. And then whatever is left, no matter what it is, it's going to react together with each other. So the main focus, whenever you're writing an equation like this, main focus should be on H and OH. So I'll give you another example. Let's suppose I have C2H7, COOH. Now, it is possible that at this stage you might not have seen this if you're somebody in grade 10 or grade 9. But that doesn't matter, because what matters is this H positive ion. As long as you have that, you can treat it as an acid. So let's suppose I reacted with sodium hydroxide. So what will happen is this H and this OH is going to react, and that's all you need to care about. Anything else that's there, just combine it. So obviously this is left from the acid part, I just write that. This is left from the base part, I write it that. And there you go. This is a negative ion, that's a positive ion. And how do I know that's a negative ion? Because this is H positive. So obviously this must be negative. And this must be any negative, any positive, and that's OH negative. So I can simply see based on this that I'll get this. This is also salt, but it's an organic salt because you were reacting an organic acid. And these are called esters, organic salts. But regardless, we know what is actually happening. Now, obviously, this reaction is going to be much slower than the reaction of HCl and sodium hydroxide. But you cannot use it to differentiate between HCl and a weak acid because there is no visible observation here. You see, the salt that is made, it is soluble in water and it's colorless. So you won't actually see a color. Even if water has sodium chloride in it, there's no way to confirm that it has it as long as it's dissolved. We can crystallize it, sure. But if you crystallize the other salt, that will also give us white crystals. Similarly, acids are colorless, bases are colorless. When they react together, it's a colorless reaction, no gas coming out. So this reaction is not suitable if you are going to design an experiment to check for something. Sure, if you want to actually make sodium chloride, this would be good. And we will talk about on Monday that what are the best ways of making salts. But this reaction, because it doesn't have any visible changes, the word is visible changes. That's the key word. There is no visible change in this reaction. So this is a bad choice if you're trying to differentiate between a strong acid and a weak acid. A much better way would be to react them with, let's say, sodium, because it's going to give us hydrogen gas and we can see the bubbles. Similarly, a much better way would be to use electrical conductivity as a test, or to use litmus. Oh, sorry, not litmus. My bad. Not litmus, but a universal indicator or a pH paper on a way to check pH, but not this reaction because there is no visible change. All right. So that's how acids and alkalis react. Now, what happens if you have acids with bases that are not alkalis? So there are two different types of those. One is you have metal oxide, and one is you have metal carbonate. Metal carbonates can be basic, or they can be amphoteric. But in either case, they will still react with acid. The, I just said a word. I'll define it. Amphoteric is basically anything that reacts as an acid or as a base based on what it's reacting with. Now, water is not amphoteric because it reacts as acid and base at the same time. But amphoteric things can choose what they're going to react as. They can either be fully acidic or they can either be fully basic when they're reacting. Okay. Water, on the other hand, is playing both sides, acid and base. So it is neutral. But amphoteric things are not that. So an example of amphoteric salt would be aluminum oxide. It can react with sodium hydroxide. In fact, it is used when we do electrolysis of that to take away all the impurities away from Al2O3. We actually reacted with sodium hydroxide. So it can react as an acid. On the other hand, it can also react as base if you reacted with acid. Obviously, those reactions are not in our syllabus for now. We will do study them in A levels. So the key word here is amphoteric that you have to know, and this is just an example. Okay. Zinc oxide is also amphoteric. Lead oxide is also amphoteric. Many lithium salts are also amphoteric. But regardless of whether they're amphoteric or not, when they react with acid, they will produce salt and water. But one extra thing that carbonates produce is carbon dioxide. We have talked about this in detail earlier on as well, that carbonate actually has carbon dioxide trapped in it through a chemical reaction, which is why that when given the chance, this carbon dioxide simply leaves and goes away. Okay. So that's a reaction. Now you can write ionic equation for some of these reactions. For example, if I were to react, let's say take this example, HCl reacting with NaOH. So it produces water and sodium chloride. Okay. So the first thing you need to know is state symbols. So HCl is aqueous, sodium hydroxide is aqueous, water is not aqueous, water is liquid, and sodium chloride is aqueous. Next thing, as I've told you already, whenever you want to write ionic equation, ionize everything that is not solid, liquid, or gas. That's it. So HCl is aqueous, it will ionize. Sodium hydroxide will ionize. Water will not ionize. Sodium chloride is aqueous, it will ionize. So we just cancel the things that are not changing. You can see that chloride here, sodium here, sodium here. They are not changing. These are spectators. They are not actually taking part in a reaction. But what is taking part in the reaction? The H positive and the OH negative is taking part in the reaction. So we'll write that H2. And that's your ionic equation. Okay. And that is showing the actual reaction that happened. In fact, this reaction is called neutralization. This reaction is so common that it has a name for itself. When H positive goes and makes OH negative. Okay. All right. Oh, sorry. It reacts with OH negative to make water. So that's this acid-base reaction. The last one that I want to talk to you about is the reaction of ammonia gas. Whenever ammonia reacts with acid, it doesn't just accept H positive, it actually binds to it. So it forms ammonium chloride, for example. Okay. So what's going to happen is that this is not ammonia, it's ammonium. Okay. And that ammonium is going to be a part of that acid now. So the acid changes to salt. Okay. So that's how ammonia's reaction differ from other bases reaction. That in all the other bases, what we have is that they are losing OH negative or they are accepting H positive, and they're forming new things, salts, and also water or carbon dioxide or something. But in the case of ammonia, it does not form something else. It simply forms one salt. So how do you react it? You simply take this ammonium and you react with any H that you have. So for example, if I have 2H, I will need 2 ammonia. So this H is now being replaced with ammonium and I will need 2 of them. Because I have 2H, I'll take 2 ammonium now. Okay. Similarly, if you have, let's say, if you have something else like H3PO4 and for some reason it reacts completely, you have 3 hydrogen, it will take 3 ammonia. All right. So that's how ammonia's reactions are and how other salts, other acid and bases reactions are. First one is oxides. There are 4 different kinds of oxides. These oxides, obviously, they are compounds of oxygen. And when oxygen reacts with oxygen can react with both metals and non-metals. When it reacts with metals, it forms metal oxides, and when it reacts with non-metals, it forms non-metal oxides. Now, these behave differently as far as their acidic or basic nature is concerned. Metal oxides can be basic or amphoteric, and non-metal oxides can be neutral or acidic. Okay, so 4 different kinds of these acids and bases. Now, as far as your syllabus is concerned, you just need to remember that for amphoteric oxides, you have lead oxide, you have zinc oxide, and you have aluminium oxide. Aluminium, zinc, lead. These are the 3 that form oxides that are amphoteric, and you have to remember that. The rest of them that are in your syllabus, like copper oxide, iron oxide, lithium oxide, sodium oxide, calcium oxide, magnesium oxide, they are all basic. If something else is amphoteric, they will tell that in the exam. So you don't have to memorize it. I'm not saying that there's no other amphoteric oxide. I'm just saying that if there is, they will tell you about that in the exam. Similarly, for neutral side, on the non-metal side, we have carbon monoxide, we have water, we have calcium monoxide. These 3 non-metal oxides, these are neutral. अब इसका पता कैसे चलेगा? You just first identify any oxide that you have. How do you identify it? It has oxygen in it that is joined to, that is bonded to one other element. Sulfate नहीं बोल देना, because H2SO4 sulfuric acid, it does have oxygen in it, but that is part of sulfate. उसमें 3 elements हैं. It's not an oxide. Sodium nitrate में oxygen atom जरूर है, but it's not an oxide because it's part of 3 elements joined together. But take that NO2, that is nitrogen and oxygen, oxide, CO2, oxide, MgO, oxide. Now what happens? Once you have identified something to be oxide, you then see whether it's joined to a metal or non-metal. तो आप देख लेते हो कि अच्छा मेटल है या नॉन मेटल है. अगर मेटल है तो बेसिक होगा या एम्फोटेरिक होगा. कैसे पता चलेगा? एम्फोटेरिक की लिस्ट याद कर लें, 3 तो हैं, और देख लें अगर उनमें से है तो एम्फोटेरिक है, नहीं है तो बेसिक. Unless they tell something extra in the exam. Similarly, न्यूट्रल में ये 3 है, इनके अलावा कोई है तो हमने उसे एसिडिक ही अज्यूम करना है अगर वो नॉन मेटल का है. तो सल्फर डाइऑक्साइड acidic, sulfur trioxide acidic, carbon dioxide acidic, nitrogen dioxide acidic, क्योंकि they are not in the neutral list. So ये 6 आप याद कर लो, बाकी ऑटोमेटिकली आप फिट कर लेंगे. So that's for oxides. And the last thing that we need to know is soil pH. The pH level of soil is very important that it is controlled, because you see, plants grow in soil and plants are living things just like us. Now, as we need an optimum pH level for our body to function, for example, our blood has a specific pH range in which blood can transport things and blood can function well. अगर उसकी pH change हो जाएगी, we will not be able to survive. Similarly, our stomach has acid in it which allows us to digest. अगर उसकी pH change हो जाएगी, अगर वहाँ पे हम उसकी pH increase कर देते हैं, तो हमारी digestion खराब हो जाएगी, problems आ जाएंगी. So that's just one example of how pH affects living things. Just like that, uh, you have bacteria. Let's suppose you have a swimming pool and you add chlorine to it. That chlorine is going to react with water and form an acid, and that acid will lower the pH of that swimming pool. So it will kill all the bacteria. So when you go swimming, they don't damage you, they don't harm you, those bacteria, because they're dead. Okay. So just a teeny tiny amount of chlorine will do that. So pH is important for things to function well, and pH is also important for things to just survive. Just like that, for plants, pH plays an important role because they extract their salts from the soil. They extract their nutritional, all the nutritional benefits that they have from the soil. So अगर pH change हो जाएगी, वो salts वहाँ पे react भी कर सकते हैं, वो salts वहाँ से leach out भी कर सकते हैं, उनको absorb करने में मुश्किल हो सकती है, or this plant themselves can be damaged. So if you have acidic soil, we add calcium oxide to it. Calcium oxide, because it's a metal oxide, not in the amphoteric list, it is basic. So हम उसमें calcium oxide या calcium hydroxide add करते हैं. Sorry. And if you have if you have basic soil, for example, soil में बहुत ज़्यादा calcium oxide आपने add कर दिया था, then we will need to make the pH low, and for that we will need H positive. Okay, so we will do something to reduce the pH. Now how do we do that? We basically, what happens is that you have acidic soil, you take calcium carbonate, which is basically limestone, you crush it, you add it. Why do you crush it? Because you want it to have higher surface area, so it reacts. You need to have smaller powder particles in it. बड़े ब्लॉक्स होंगे तो उतनी जल्दी रिएक्ट नहीं करेंगे. ठीक है. ऑल्सो इसका एक फायदा ये है कि बिकॉज इट्स इनसॉल्युबल इन वाटर, जितना रिएक्ट करना होता है वो कर जाता है, बाकी पड़ा रहता है. बट ऑब्वियसली दैट क्रिएट्स मोर प्रॉब्लम. सो एक और काम हम कर सकते हैं, दैट यू कैन यूज कैल्शियम ऑक्साइड एंड कैल्शियम हाइड्रोक्साइड, स्लेक्ट लाइम, ओके, और जस्ट लाइम. सो बट देन व्हेन यू आर एडिंग दैट, आपको बहुत ख्याल करना है कि आपको जितनी चाहिए उतना ही ऐड करें आप, क्योंकि अगर आपने ज़्यादा ऐड कर दिया, they are soluble in water, they will pass through the soil and they'll get absorbed there, which means the soil will now be alkaline. वो एक नया मसला बन जाएगा. So we try to keep neutral, we try to maintain the pH, and for that we have the whole lime family, 4 things in there, जिनमें से 3 हमें help out करती हैं. All right, so that's about soil pH, and those are all the concepts that you need to know for acids and bases.